Welcome to this lecture. In this lecture on plate fin heat exchanger, we are going to talk about the analysis of plate fin type heat exchanger, and in this one we will first start with the fin equation, where you might have noticed that we have so far in case of plate fin type exchanger, we have talked about the separating plates, and in between the plate what we have is basically some fin connected between this one. Between the two separating layers we have fins joined, and we have talked about the bridging between this plate and the separating plate and the fin, and we have ensured that there is a good thermal contact between the plate and the fin. So, now if we look into it carefully, what we have is basically a separating wall, and each individual this layer we can think it as a fin connected between the two separating plate. So, what we need to analyze finally, or what it eventually comes as, this is some plate at T temperature T A and some plate at temperature B, depending on the type of fluid, and we have like two plates connected by a separating this is a fin which is connected between the two plates. So, we need to analyze this one, or already if you have analyzed this kind of fin equation, where most of the time we see that the we have a plate and we have a fin, and the one end of the fin is at a particular, either it is at particular temperature, or we often consider that this fin is having an adiabatic tip, that is very common, and sometimes we often assume that the fin at this end it is communicating with some fluid, and it is thermally communicating with some fluid, and there is some heat transfer H between this fin tip and the surrounding. We also often use that this fin is also at a particular temperature, some temperature T infinity or some other temperature. So, this is typically T base, and the fin is connected to T base, and this is how it is looking like. So, here in contrast to this one, we have another fixed plate, and we have designated as T A and the T B, two different temperatures. So, similarly, if we look at the complete assembly, we will find that there are different type of layers of fins, and this is like this, say this is designated for fluid 1 and this is fluid 2, this is again fluid 1 and fluid 2 and so on. But eventually if you look at, you will finally be solving at any time, and say there will be say T wall 1, T wall 2, T wall 3 and so on, T wall 4 and T wall 5, like that it will continue in the actual exchanger. But for a particular layer, for this particular layer, on one side we have fluid 1 and this other side we have between fluid 2. If we consider this fluid 2, on one side it is having fluid 1, on the other side it is having fluid 1, and both the sides it is having fluid 1. Similarly, if we consider this fluid 1, on either side of it is having the fluid 2. This is particularly the case in a symmetric configuration of two stream heat exchanger, where most of the time you will find that we have a combination like 1 2 1 2 1 2 and so on. But often it may so happen that depending on the amount of fluid we may not be able to equally distribute it among the each two layers. So, that we will consider later on, where sometime we need to put it like 1 2 2 1 2 2, where if we have more amount of fluid, so we put it in a double bank, we call it. So, that configuration we are not considering at this moment. So, basically we are looking into this configuration, where alternatively fluid 1, fluid 2, fluid 1, fluid 2, like that we have they are arranged. So, basically it boils down to a situation where we have two separating plate and a fin connecting between the two plates. So, if we have to analyze it, we have to analyze this basic phenomena, where a fin is connected between the two separating walls at different temperature. Now, if we have to do that one, let us look into that in details. Then we have a configuration like this. We have separating walls, and this is, say, this side is this is the fin, and this fin is connected to a temperature T A, and this side is connected to temperature T B. Now, if we try to solve that fin equation, what we do is that we take a small section of this one, and we it is actually a 3-dimensional, this dimension we are not drawing. This is how it looks like, this is the separating plate, and this is how it looks like. We have taken a small section of this fin in, this is say x direction, and this is between x and x plus dx. So, within the small element of this fin, we have considered a small element dx between x and x plus dx. So, we have qx amount of heat, conduction heat getting transferred, and this is going through this element q x plus x dx, and in between we have some kind of fluid which is taking this heat. So, we have q convective. So, whatever heat that is coming through the fin, the convective fluid flowing on top of it, on top of this fin, is taking that amount of heat. So, if we now have to make an energy balance, what we find is that q x amount of heat is getting distributed to q x plus dx, and we have also q convective term. Now, if we look into this q x plus dx, you will find that q x plus dx can be written as q x plus dx. We can write it as q x plus dqx dx into delta x. So, we have considered a small element delta x. So, we have, this is how it is getting distributed. So, we have already talked about q x is equals to q x plus dx plus q convective. Now, from here what we are getting is q x plus dx minus q x plus dx minus q x is equals to dqx dx into dx. This is what we are getting. Now, this q x plus dx minus q x is nothing but dqx dx with a negative term. So, this will become dqx dx multiplied by dx with a negative term, and that will become plus q x plus dx minus, this will become q convective is equals to 0. This is q x plus dx minus q x, okay, and q x plus dx. From here, if we look at q x plus dx minus q x is equals to minus q convective. So, that is what we have written here, q x plus d x is equals to minus convective, and then we have the dq dx part. So, this dq dx with a negative this part can also be written as this can be written as dq dx. We can write it this dq q x dx is equals to, we can write it as d dx of minus k into a into dt dx. So, this is what is the convective heat transfer, and if we put it in this equation, what we will find is that q convective term is that q convective plus d 2 t d x square with k and a. These are the two terms we will have for this is equals to 0. So, if we have these terms, what is that Finn equation we are looking at? This is for this cross section we have where the heat is going q x and this is q x plus d x, and this is where we have q convective. So, how much is the q convective heat transfer? Q convective is basically h into the area. What is that area? And h a T minus T infinity. T infinity is the fluid temperature, and this area is basically nothing but the perimeter multiplied by this dx. So, here also we have that dx part. Now, if we put into this equation, we will find that this is giving you d 2 t dx square into k a, and then you have that delta x term, and then we have that h into a into t minus t x t infinity, and that a we can write it in terms of the perimeter multiplied by the dx. So, this will make the total equation d 2 t this is dx square is equals to this is h upon p by this k into a. This a is nothing but that cross sectional area through which the conduction heat was taking place. So, that is about, if we talk about this direction as w, then we have w plus this is the thickness of the fin t. So, we have w into t as the one, and we have then t minus t infinity, and both sides this dx and this dx are coming out. So, this is equals to 0. So, what is about the sign? We have that this is equals to if we put this perimeter p, if we put this perimeter p, if we look into this, p is nothing but w plus thickness multiplied by 2, and if we arrange it here, you will find that h into p is nothing but 2, and then we have w plus t divided by w into t, and of course, we had that k part here. So, there has to be a k here and we should have k here. Now, in often we make an assumption that this thickness of the fin is very small as compared to the this W. So, we call it thin fin approximation, thin fin approximation we call it approximation. So, in that case we neglect T as compared to W. So, in that case we will have twice H W by K W and T. So, this W and W will cancel. So, we will have twice H by K and T. So, this we will call it as d2t dx square minus m square into t minus t infinity, that is equals to 0. So, now if we look into this equation, we have d2 t and we put deliberately this is a constant, the fluid temperature flowing over the fin, we assume it to be constant. So, we have this is minus m square and t minus t infinity is equals to 0, where this m square is nothing but 2 h by k t, in general it is h p by k a, or for thin fin assumption this is root over m becomes root over 2 h by k t. So, this equation we can shortly write it to be d2 theta dx square is equals to m square theta, and this is the fin equation where this fin is subjected to convective fluid temperature, dissipating heat through the convective heat transfer. Now, if we have to solve this equation, we know the solution of this equation, in general equation theta x. What is theta? Theta has been considered to be T minus T infinity. So, T is basically the temperature at any location in that fin. This is at T A and this is at T B, anywhere between this one at a location x, we consider this temperature to be T x. So, this is the temperature T x minus T infinity. So, that this theta A we call it as T A minus T infinity, and theta B it will be T B minus T infinity. So, now we are trying to look for a solution of this equation, and we know what is the solution. The theta x, or theta basically is equals to some constant into e to the power m x plus some constant of e to the power minus m x. Now, we have two boundary conditions appropriate for this equation, and from where we have to get this constant C 1 and C 2, and already you have learned how to do that in your earlier classes, probably where we have assumed that one of the fin is at constant temperature T A, the other end is at adiabatic condition. So, in this case where we have at x equals to 0, we consider it to be theta equals to, as we have said, theta A, and at x equals to L we have theta equals to theta B. This is what we have assumed, that between the two end the temperature is T A and T B. So, if we solve this equation, we will find, or if we apply these boundary conditions, so we will find that C 1 comes to be C 1 comes to be theta a multiplied by 1 minus omega, and C 2 becomes theta a multiplied by omega, where this omega is nothing but is e to the power m l minus r by 2 sin hyperbolic m l, where L is the length between the two, I mean the fin length. So, this is the fin between T A and T B, and we have this omega is equals to e to the power m l by minus r by 2 sin hyperbolic m l, and C 1 and C 2 are like this. These are the constants we have evaluated for this equation theta x. So, the overall equation, and what is R? R is nothing but a ratio between theta b by theta a. So, there are other forms of expressing this fin equation. This particular expression of fin I mean solution or fin equation solution we have taken from B.S.B. Prasad's paper. So, now if we look at, we have the complete solution theta x is equals to theta a multiplied by 1 minus omega, and that multiplied by e to the power m x, this is e to the power m x plus omega into e to the power minus m x. This is what is the complete solution. Now, if we have the knowledge about the fin temperature profile over the fin. So, this is what we have, the T A and T B, and we have the knowledge about the fin temperature profile theta x known, and this is of course not T A, we call it theta A and theta B. So, this is at T A and this is at T B, and we know now the temperature profile over this fin. So, once we have the temperature profile known to this fin, we can try to estimate what is the total amount of heat being dissipated through this fin. So, if we try to do that one, we find that total amount of heat getting dissipated over this fin length is 2 into h into theta x into dx, and this is integrated over the length 0 to L. Why this 2 factor is coming? Because we have this surface, we have this surface, and over this surface we have the heat transfer coefficient h, and what is theta x? Theta x basically is the temperature T x minus T infinity. So, that T x minus T infinity heat transfer coefficient and the dx. So, that is how you know that if we consider an element dx over this length, and that length has to be integrated over the length 0 to L. So, that is how we will get the total amount of heat getting transferred through this fin over this length L, or this is basically a small l. So, this is, if we are trying to evaluate this one, we will have an expression of q t is equals to 2 of h by m into theta a plus theta b. If you put that value of theta x and then you integrate, you will have an expression of tan hyperbolic m l by 2. So, now what we do is that we divide and multiply both sides by m l by 2. So, that way what we will get is m l by 2 on this side, and then we have 2 h by m, then you have theta a plus theta b, this term is there, and tan hyperbolic m l by 2, and here we have multiplied it and divided it but this tan hyperbolic ml by ml, this is nothing but the fin efficiency. So, we can write it as this 2 and this m, they are going out. So, you have h into L, then you have theta a plus theta b, and then we write it as eta. This eta as if is for L by 2. So, we call it fin efficiency of the half of the fin. So, now if we look at, we have the heat transfer, the total amount of heat transfer, that q t, the total amount of heat getting dissipated through the fin is h into L, and then you have theta a plus theta b and multiplied by eta half or half fin efficiency. Now, if you carefully look into it, we can write as if this is h into L and then theta a and then eta half, and so this is one part, and the other part if you look at, it is just nothing but h into L and then theta b and then eta half. So, as if we have this contribution of half of the fin, this L and then half of it is contributing with theta a, and this is where we have the theta b. So, this is just nothing but T b minus T infinity, this theta b, and this theta a is nothing but T a minus T infinity. So, as if we have half of the fin contributing to the fluid A and the other half is connected to the other fin. So, this is basically nothing but the half fin idealization of the plate fin heat exchanger. So, this is again, this is I mean a good assumption particularly for a 2-stream heat exchanger, but when we have multiple streams or we have a different asymmetric fin, we find that there is I mean good deal of violation of this one, and we will then we need to look into a different analysis during that time. So, the total heat transfer is getting I mean as a half of that fin connected to surface A T A, and the other one is connected to T B. Thank you.